Hello everyone, welcome again. So today's lesson will be on the energy module in Year 11 Chemistry. And in today's lesson we're going to look at a first-hand investigation to see the effect of factors on reaction rate. So we're going to look at how different factors affect the reaction rate of a particular chemical reaction. Okay? So the aim here is to observe the impact of various factors on reaction rate. Okay? So we're going to look at temperature, concentration of reactants, and size of solid particles as the factors to be tested. Okay, so we're going to look at, does temperature affect the reaction rate and how? Does concentration of reactants affect the reaction rate and how? And also the size of the solid particles, does that affect the reaction rate? Okay. So what we're going to need is 0.1 mole, 1 mole, 2 mole, and 4 mole hydrochloric acid. We need magnesium strips. We need water of varying temperatures. We need beakers, test tubes. Okay. So the first one we're going to do is we're going to look at how temperature affects the reaction rate. So what we're going to do is place 5 mils of the 2 molar hydrochloric acid in each of the 4 test tubes. Okay. In this case we have 3 in the diagram, but you could have 4 just at another temperature. Could be 70 degrees maybe or something. Okay. Now, place the test tubes in hot water baths held at different temperatures, 0, 25, or 50 degrees. Probably not 0, I'd probably say maybe go 10. If you could manage 0, that would be really good. But, 10 degrees is fine also. So any set of temperatures is okay, as long as you can get them. As long as you note down what the range of temperatures is, that's okay. So you can pick any temperatures you want, really. So once you've got the hydrochloric acid in the test tube and the test tube inside the water, you place a 3 centimeter strip of magnesium in each tube and measure the time for the magnesium to completely dissolve. Okay? You could probably do them one at a time as long as the temperature of the water stays constant. So if you can manage to keep the water at constant temperature, you can probably do this one at a time. If not, you have to organize some kind of multiple timing mechanism. Okay. So what you have to do also is ensure that the test tube is agitated at all times. So just to keep it well mixed, in case you get situations where some of the magnesium isn't exposed to the hydrochloric acid. So just make sure that it's sort of agitated every now and then. Okay. So you're just measuring how long it takes for the little piece of magnesium to completely dissolve in the water, in the hydrochloric acid, sorry. Okay. So the next one is the concentration of reactants. So if you look here, you've got 0.1 mole, 1 mole, 2 mole, and 4 mole per liter acid. Okay. So you can systematically dilute hydrochloric acid solutions to produce solutions with the following concentrations, so the ones that I just mentioned. Or if you already have them on hand, don't bother diluting them, just use the ones you have on hand. But more than likely you probably won't have all of these. Actually, you might. So try to look for the ones that you have on hand. Again, these numbers are arbitrary. You don't have to pick a particular, you don't have to use these numbers. So if you have a pretty wide range of concentrations in your lab, you might as well use that wide range. Just note down the numbers, okay? Place 5 mils of each solution in a separate test tube in a test tube rack, and add in turn a 3 centimeter strip of magnesium to each tube and time how long it takes for complete reaction. Again, you're just doing the same thing as you did in the temperature one, seeing how long it takes for the magnesium to completely dissolve. And what you'll notice is the one with the most concentrated acid will have the most bubbles, and it'll probably happen the fastest as well. And obviously the one with the lowest concentration will have less bubbles, and it'll take a lot longer for this magnesium to completely dissolve. Okay? If at all, if it completely dissolves at all. Okay? And lastly, there's the size of solid particles. So you place 5 mils of the 1 mole per liter hydrochloric acid in each of the 2 test tubes. We're only using 2 in this case because it's not really easy to kind of uniformly change or in a controlled way, change a big lump into a small lump. So we're just going to look at qualitatively in terms of the lump size. Okay, so we're just going to look at it like this: a big lump of coal or powder. Okay, so it's not a gradiated experiment in this case. Okay, so you place 5 mils of the 1 mole hydrochloric acid in each of the test tubes. Then wrap a 3 centimeter length of magnesium into a tight ball and time how long it takes to dissolve in 1 tube of acid. So in this case, we're not putting it in as a strip. We're going to put it into a little ball and dump it in the acid, sort of like this shape. Take another 3 centimeter piece of magnesium and cut it finely into tiny pieces. So you try to cut it into as small a piece as possible, but don't lose any of the pieces, okay? Otherwise that's going to stuff up your experiment. Make sure you cut it in such a way that you can keep all of the pieces. Maybe cut it on a piece of paper or something so you can quickly collect all of the little pieces. And add the pieces to the second test tube of acid and time the reaction, okay? So you're going to see how long it takes for the tiny pieces to react compared to the big lump, okay? So what results are you going to see? Well, the higher temperature, the more effervescent the reaction, and the more rapidly the magnesium dissolves. Okay, that's pretty obvious. The higher the temperature, the faster the reaction rate, right? So that's what you're likely to see in the temperature one. So the highest temperature will have the highest reaction rate. In experiment B, concentration of reactants, the speed of reaction is much higher for the higher molarity acid. In the most dilute acid, the reaction is very slow. So for the very concentrated acid, as I showed you before, the reaction rate will be very high, and for the very dilute acid, it'll be very low. And that can be seen by the bubbles, and also at the speed at which the magnesium dissolves. Okay, so the magnesium will dissolve very quickly in the very concentrated acid, and it will dissolve very slowly in the very dilute acid. And in part C, the results you're likely to get in the size of solid particles experiment. The slivers of magnesium react rapidly, but the larger ball of magnesium reacts very slowly. Okay, so the ball of magnesium will react a lot slower than the chipped up pieces because of the surface area exposed. Okay, so that's what you're likely to see. Okay, so now that we've gone through the basic results, just quickly look at the safety related things with this prac. So obviously the concentrated hydrochloric acid solution is a big concern. So just be very, very careful when you're dealing with it, or mostly your teacher will dole out the formol stuff to you, but just be aware of that. And in lieu of that, we have to sort of know that gloves, aprons, and goggles need to be worn at all times, just so you don't get any of the acid on you, okay? Okay, the evolution of hydrogen gas could pose a safety concern. So each of these reactions produces hydrogen gas. It's probably not enough from one experiment to cause any serious concerns, but maybe if there's, 5 or 6, maybe 10 of you working on the same experiment, that could produce a fair bit of hydrogen gas. So we don't want to hurt each other we don't want any possible fire hazards. So make sure to complete the experiment in a well-ventilated area. So there's nothing toxic in this prac. So there's no harm in keeping the windows open so that some air can get in and the hydrogen can find its way out of the room as well. Okay. So make sure that you do this in a well-ventilated area. Ideally a fume cupboard, but if there's more than one group doing this, you probably don't have more than one fume cupboard, though you might. So it's a good idea to just do this in a well-ventilated area. Okay. So that concludes today's lesson on this fairly simple prac. We looked at the 3 type pracs that we can go through: size of particles, concentration of reactants, and temperature of the system. And we looked at the possible results that you're likely to get when you do this prac. Okay, so move on to the question segment now. Okay, so explain the variable reaction rates of combustion reactions in terms of particle theory. Okay, so how can we explain the variable combustion reaction rates? this is more of a general question rather than one specific to this prac. Well, the rate of collisions between particles determines the speed of chemical reactions. Okay, we've known this for a while now when we talk about particle theory. So slow combustion occurs when oxygen reacts with solids such as aluminium and iron. And while oxygen is a gas, so its particles move freely and can collide with the exposed metal surface particles. Okay, so oxygen can move freely, whereas metal atoms cannot. However, metal particles are held in a lattice, so they're not free to move. Okay? Thus, the collision of particles occurs at a slow rate, and the reaction is consequently very slow. Okay? Now, faster combustion reactions occur when gases are mixed with oxygen gas, because their particles are constantly moving at high speed. Okay? So that one, they're mixed together, allowing lots of different particles to collide, but also they're moving at high speed because they're gases. This means that there are more frequent collisions, creating greater possibilities that the particles react with the sufficient energy, collide with sufficient energy to react. And these reactions are often explosive. And explosive reactions can also occur between oxygen and solids if the solid is ground into fine pieces. This makes a large surface area available, and hence the number of particles available for reaction and collisions is greater. Okay? So the variable reaction rates in combustion is basically because the particles' mobility is different in different fuels. So if it's a gaseous fuel, the particles are very mobile, they can mix with the air, and when they can collide with the correct energy, so they will burn. But with a solid, they don't move as much, simply because they're locked in the solid's form, and so they can't collide as frequently, so you get a much slower combustion. Okay? So explain why increasing the temperature of the reaction increases the reaction rate. So this is directly related to our prac now. We're looking at, well, why does increase, so now that we've got a result from the experiment, how do we explain that with our chemistry model? And that's what science is all about. We use science to explain what we see in the lab. Often students think that we use the lab to explain what we figure out in science, but my physics lecturer from first year, Professor Joe Wolf, once told me in a lecture that everything we see in the lab, science was developed to explain. Okay, so it's always in that direction. So that's what we're going to do here. So increased temperature equates to an increased kinetic energy of the particles. Okay, so an increased temperature equates to greater energy in the particles. This means that more particles are likely to achieve the correct energy to react. Okay, so if the temperature goes up, then the particle's energy goes up, which means that the particles will more likely have the correct energy to react. They're much more likely because there's more energy available. And that means the reaction rate will go up. Okay, because now more particles are in the state where they have enough energy to react. So if more particles have the energy to react, there will be more collisions with the correct energy, and which means there'll be more reactions. Okay? Question 8, explain why the smaller magnesium pieces reacted faster than the ribbon or the ball. So by cutting the magnesium into smaller pieces, there's more surface area. Okay? This means that there are more magnesium atoms exposed to the HCl, which results in increased reaction rate. So if, for instance, there was 4 magnesium atoms in the ribbon, if we cut it in half, actually let's not pick 4, let's pick like 6. Okay. So if you imagine this now, if we cut it like that, then all of these, you can see that the only part that's not exposed to the oxygen is the part between here. So you can see there's way more surface exposed to the acid than there was before. So if we cut it up into smaller pieces, there's a lot more atoms available to react because there's more atoms on the surface, and so they'll collide with the HCl and react. So by cutting it up, we get much more surface area, and that means much more atoms on the surface, which means more reactions. Okay, so faster reaction rate. For the size of particle experiment, other than the concentration of the acid, what must be kept the same for the results to be valid? Okay, so for experiment C, okay, one is the total mass of magnesium used. So if you use 5 grams for your ball and 1 gram of chopped up magnesium, that's obviously not a valid experiment. So if the magnesium is different, if the mass of magnesium is different, the results are not comparable, unless of course you normalize, but again it's still not comparable because one is chopped up and the other one's not. So larger masses of magnesium will take longer to dissolve than pieces of magnesium, okay? Pieces of small magnesium. So larger amounts will simply take longer to dissolve, and that's a consequence of the conservation of mass, okay? So in the temperature experiment, name 3 variables that need to be kept constant. So three controlled variables is what we call them. So again, mass of magnesium is one. The shape of the magnesium ribbon, this one's hard to control, but of course if you've got a ribbon, it's pretty much the same shape. But as long as you're not using like a square compared to like a circle or something like that, then that's okay. And also the concentration of the acid, so that's a major one. If the concentration of the acid's different, obviously you're going to get different reaction rates. Okay, so those are the 3 things. So that concludes today's lesson on the first-hand investigation for factors that affect reaction rate. We looked at 3 practices that you can do in your lab that involve reaction rates. So modifying the temperature, changing the concentration of reactants, or changing the size of reactants, size of solid particles. And we looked at the typical results and safety issues associated with this prac. So the next lesson we're going to look at explosions and the safety regarding explosions. So I look forward to seeing you at our next lesson.